So hello everyone, welcome to the UNC Core Center for Clinical Research Speaker Series for May 13th, 2020. We appreciate you joining us for today's talk. Our presenter today is Dr. Michael Hudgens, a professor in the Department of Biostatistics at UNC Chapel Hill. He is also the director of the Biostatistics Core of the UNC Center for AIDS Research. His presentation today is titled Causal Inference, a Gentle Introduction. So Dr. Hudgens, whenever you're ready to start, feel free. You're still on mute, I think.
Okay, great. So thanks for the introduction and thanks for the invitation to give this presentation. I'll go ahead and get started. Right, okay, so the goal of this presentation for this hour is just to give you a gentle introduction to causal inference if you are not familiar with this area, or maybe you've heard about it, but you'd like to learn a little bit more. And the main distinction here between what we're going to be talking about and what we might do in more traditional statistical analyses has to do with the distinction between association and causation. And most of the time when we're conducting scientific studies, we have one of two goals in mind. One is just to assess whether or not associations exist between particular variables, or if we can predict certain outcomes on the basis of other outcomes. But in other instances, one of the goals of the scientific inquiry is to determine factors that cause or have an effect on the outcome of interest. And in our training, we're often told that association does not imply causation. But the question becomes, under what circumstances can we conclude that if we see an association in our data, that it really is due to causation? So this area of causal inference provides an answer to that question. In other words, it makes precise, in a mathematical or statistical sense, under what conditions we can conclude that associations we see in our data are actually potentially reflective of causation. So I'd like to spend today introducing some of the fundamental concepts in this area of causal inference. It's a really interesting field. It's very broad. It's an active area of methodological research, which includes statisticians, biostatisticians, epidemiologists, folks in economics, political scientists, computer scientists, and so on. So it really cuts across disciplines. On one hand, it can be very philosophical, and then at sort of the other end of the spectrum, it can be very technical from a statistical or mathematical perspective. One of the differences between causal inference and some other areas of statistics is there's a real focus on sort of what I call the front end, which is very carefully articulating what the estimands or parameters are that we're trying to draw inference about. In other words, what exactly is the question? When we say we want to know if an exposure has an effect on disease, what exactly do we mean by that from a statistical standpoint? What is the parameter we want that would capture that effect? And then going from, after carefully defining the estimands, thinking about assumptions that are sufficient or necessary to identify those parameters, meaning under what assumptions can we draw inference about those parameters? Whether or not those assumptions are subject to empirical test or not. And then after sort of those steps, then we move into more familiar domain of statistical inference. So this is an area that's really gained currency in many different subject matter areas. Certain areas, it's really kind of fundamental. Epidemiology being one. Epidemiology meaning the word meaning the study of disease etiology or causes of disease. In econometrics, comparative effectiveness research, implementation science, many areas where you really want to understand the causal effect of a treatment or an exposure or a policy. So you see these statistical methods, which have been developed over the last few decades, now being deployed in a wide array of subject matter areas. I've just, on this slide, pulled a few papers from journals that maybe many of you are familiar with, given that you're in an arthritis center. All of these using relatively modern causal inference-based methods, these three that I'm highlighting using propensity score-based methods. And I'll talk today a little bit about propensity score-based methods. If you're not familiar with these, at least introduce you to the idea behind what's underneath the hood of the analysis of some of these papers. As I said before, this is also an active area of statistical methodological research, I think partially because these methods apply to so many different areas. This is just a smattering of papers that came out in the last year in each of the leading statistical journals in our field. So very exciting area of research. All right, so with that as background, here's the sort of roadmap for the next 40 minutes or so. I'm going to introduce the notion of potential outcomes or counterfactuals. This is an idea that dates back to Jerzy Neyman about almost 100 years ago now. And then using this Neyman potential outcome model for causal inference, Rubin and Robbins in the 70s and 80s, and then many, many others since then, have developed this into a formal area of statistical research. I'll talk about definitions and estimands, then touch on a couple different modes of inference. First, randomization-based inference, which I'll go through quickly, tying in some sort of classic results from Neyman and Fisher, and then move to the more common paradigm of inference, which is large sample frequentist inference. We'll talk both about randomized experiments and observational studies. And along the way, I'll sort of try to connect some of this to some familiar statistical concepts, such as linear regression. As I mentioned, causal inference is a very broad area, and so we can only do so much in one webinar. Many areas that I won't be touching on. I won't talk about Bayesian inference, the classic Bradford Hill criteria for causality, or any of the other topics listed on this slide. But those are, and I don't mean to diminish these as being important, but we have to make some decisions about what we'll discuss in our time. Okay, so we're going to be thinking about treatments or exposures and them having potentially an effect on a unit. The unit could be a person, a place, or a thing. In biomedical research, we typically think of the units as people. And then I'll generically refer to treatment or exposure interchangeably, but this is the thing that we'd like to assess the effect of. We could also think of this as a policy or a treatment protocol. There may be multiple aspects to this, but at sort of at a high level, we'll just refer to it as a treatment or an exposure. And so our goal as investigators is to assess the effect of this treatment compared to no treatment. And generally, we think about treatments are interventions which are manipulable. There's a phrase that you often hear in the causal inference world of no causation without manipulation. And basically this says, if you think you have a causal question, then the exposure or treatment that you're thinking about ought to be something that we can envisage that one can manipulate. In other words, another way to think about this is that even if you have an observational study, you should be able to describe the randomized trial that you would have liked to have done, even if maybe it wasn't feasible. So the sorts of questions we might ask, we might ask a causal question like, does antiretroviral therapy affect CD4 count in individuals living with HIV? And that's a well-defined question. We can certainly think about manipulating antiretroviral therapy. We can imagine people living with HIV, some of them we give ART to, some of them we don't. And then this spectrum of questions here is getting sort of moving towards variables that are maybe a little harder to manipulate. You could ask questions like, does caloric intake affect CD4 count? And again, maybe we can think about assigning individuals to high calorie diet and a low calorie diet. And then as you move further along, like we might ask questions like, does obesity affect CD4 count? Now we get into a space where it's a little harder to define how you might manipulate that. How would you sort of set somebody to be obese? How would you set someone to not be obese? Or does gender affect CD4 count? Again, kind of hard to think about maybe manipulating someone's gender. And this is, I think, down here in this region is where we get into philosophical debates. I'd like to kind of avoid these today and just be thinking about settings where it's very clear that you could manipulate the treatment. I think, in answers to Steve's question of whether or not manipulation is known by the statistician, this would probably be the sort of thing you would discuss with the investigator and kind of think through whether or not it makes sense. Again, the simplest way I find to talk about this is just, could you have done a randomized experiment? And for example, it's sort of hard to imagine randomized people to be male or female, whereas it is easy to imagine randomizing individuals to get antiretroviral therapy or not. So associated with each unit, we will be thinking about them as having two potential outcomes. One if they receive treatment and one if they don't receive treatment. So if you sort of imagine we're doing a randomized trial, before we randomize individuals at baseline, they have two possible or potential outcomes. One if they receive treatment and one if they don't. We'll refer to those as why not and why what. So why not will be your potential outcome if you don't receive treatment, why one the potential outcome if you do receive treatment. And then causal effects will be defined in terms of these potential outcomes. So at the individual level, we'll say that treatment has an effect on Y if Y1 and Y naught are different. And otherwise, if Y1 and Y naught are the same, then treatment has no effect on the outcome for that individual. Okay. So for example, suppose I have a headache right now, treatment is aspirin, and our outcome is whether or not I have a headache in an hour. So if I have a headache in an hour, I've got my two potential outcomes, depending on whether or not I take aspirin. If in an hour I have a headache no matter what, then we would say that the aspirin has no effect. On the other hand, if I have a headache in an hour, if and only if I don't take the aspirin, then we would say that the aspirin caused the headache to go away. So that would be the idea. And these potential outcomes, or sometimes they're called counterfactuals, are actually everywhere in life. We use sort of in everyday speak, we use phrases that hearken or really have potential outcomes underneath them. So you say something like, I should have stayed in bed this morning. So you're thinking of this counterfactual scenario where you were still in bed instead of being here with us today in the webinar. Gore lost the presidential election because of butterfly ballots. So you're thinking of a counterfactual scenario where there weren't butterfly ballots, and in that instance, Gore wins. You sort of see these everywhere once you start to think about potential outcomes or counterfactuals. We're interested in, typically, in at least in the work I'm involved in, questions like, does antiretroviral therapy lower viral load in individuals living with HIV? Or, maybe we ask questions like, does social distancing prevent SARS-CoV-2 infections in North Carolina? So these methodologies of causal inference methodologies can be used to answer those types of questions. And here's just a little cartoon. This fellow's going down, there's a fork in the road, and he can go down by the why not cactus or over by the Y1 cactus, those being his two potential outcomes. So we're thinking of these sort of forks in the road for each individual. So as I said, at the individual level, you can think of the causal effect as some contrast in the potential outcomes. And if the two potential outcomes for an individual are the same, we'd say the treatment has no effect, and otherwise the treatment has effect. And the fundamental problem of causal inference is that typically we don't get to observe both of these potential outcomes for an individual. Once somebody gets say, receives treatment, we'll get to see Y1, and Y0 will go missing. And so for that reason, at the individual level, it's difficult, if not impossible, to ever get a handle on these individual causal effects. So for that reason, what we tend to do instead is try to answer questions at a population level. There are a couple different ways to approach this. One way is to think of our population as n, a finite number of n units, so a fixed finite population of n individuals, and then define parameters in terms of averages across those finite number of n units. So here, this is perhaps the most common parameter that folks target, which is the average causal effect. And so all we're doing here is taking the individual causal effects and then averaging it across all the n units in our population. So you might call this a typical unit level causal effect. This is the causal effect for unit I, and then I'm just averaging across all units in the population. You could also, of course, write this as I've done at the bottom of slide 13, and which we might call this a marginal causal effect, which is to say you get the average of the Y0s compared to the average of the Y1s in the population. So another way, in other words, another way to interpret that average causal effect is what would happen on average if everyone in the population received control compared to what would happen if everyone in the population received treatment. So those are two different ways that we could interpret this average causal effect parameter. We'll use X, so we've got Y as the outcome. We'll use X to denote the treatment that individuals receive, and we'll let Y obs be the observed outcome. So that will be related to the potential outcomes by this expression, and all this says is that when an individual does not receive treatment, we observe Y0. When they receive treatment, we observe Y1. This relationship is sometimes referred to as causal consistency, which is a distinct concept from the notion of statistical consistency or convergence in probability. So as I said before, this is really a missing data problem. We get to see one of the potential outcomes, and then the other one, the potential outcome that corresponds to the treatment that the individual did not receive, that one is missing or counterfactual. Conceptually then, we can think of sort of a table of the potential outcomes for all of our units, and that's given at the top of this slide. And sometimes people refer to this as the science table or the nature table. So if we were omniscient, we would be able to see this table. We would be able to see the individual causal effects for everyone. In this case, it's an example where the causal effect on the additive scale is the same for everyone. But in reality, what we observe is the table at the bottom. We see whether or not individuals receive treatment. We get to see their observed outcome. And that allows us to fill in some of the entries of the science table, but other entries are missing. And the game then is, given just X and Y obs, what can we say about the average causal effect? So I want to touch briefly on randomization-based inference and just mention a few classic results to Neyman and Fisher, and then move to frequentist inference. And I won't talk about the third mode of inference, the Bayesian approach. So first, let's consider the ideal situation where we have a randomized experiment. Suppose it's a completely randomized experiment, just meaning that the number of individuals who receive treatment is fixed ahead of time. Then Neyman, and this is back in the 1920s, was one of the first ones to write down the potential outcomes in this way, and he was starting to think about these problems, and he proposed this estimator of the average causal effect. And this is exactly the estimator you'd think to construct. It's just a difference in sample means. So we take the sample, the average of the observed responses for those who are assigned control, and compare that to the average of the observed responses for the treated individuals. And what Neyman showed is that this is an unbiased estimate of the average causal effect. And this was in a randomization-based inference paradigm. In other words, if you compute ACE hat for each possible randomized experiment, and you take the average of those, you'll get the true average causal effect. So what we see then is that if you do a randomized experiment, association is causation. So if you see an association in your data, if these sample means are different, then that is evidence of a causal effect. And this is kind of one of the take-home messages from the webinar today, that randomized experiments, causal inference is easy, association is causation. As I said, the way when we say unbiased, we mean the expected value of this estimator is equal to the truth, and here the expectations being taken over all possible randomizations. So in this conceptualization, we've got a fixed finite population of n units. We think of the potential outcomes as fixed features of that finite population. And the only thing that's random here are the treatment assignments. So we're imagining if we had these n units and we conducted a randomized experiment over and over again, ACE hat on average gives us the right answer. Neyman's proof really follows directly from standard survey sampling results. Essentially what we're doing when we do a completely randomized experiment, you can think of that as taking a simple random sample without replacement from, say, the why nots, all the individuals who don't get assigned treatment. It's as if you're taking a simple random sample without a replacement from their why nots. And we know from survey sampling that if you take the sample average when you've done a simple random sample without replacement, that gives you an unbiased estimator of the population average. So you can sort of leverage that standard survey sampling result to derive Neyman's result. This idea of potential outcomes also gives a justification for many familiar statistical approaches that are used, such as Fisher's exact test. So suppose for a moment that, again, we've done a randomized experiment, and suppose that we've got a binary outcome. We could entertain testing the null hypothesis that there's no individual causal effect. So that is to say, y naught is equal to y1 for all I. This is sometimes referred to as a sharp null hypothesis. And it's sharp in the sense that under the null, all of the potential outcomes in the science table become known to us. In particular, recall y-obs, the observed outcome, was just y naught for folks who don't get treatment and y1 for folks who get treatment. Under the sharp null, y naught and y1 are the same. So y-obs will necessarily have to equal y naught or y1. So that means we can think of the observed outcomes under the sharp null as fixed features of the finite population. So if you write down your 2x2 table, say this is a randomized experiment with some individuals receiving vaccine, others receiving placebo, I've just written out the 2x2 table sort of generically. Under the sharp null, you can replace the y-obs with y-naughts. And the row totals here would be fixed because we're doing a completely randomized experiment. The column totals here are fixed because we think of the potential outcomes, the y-naughts, as fixed features of the finite population. So there's nothing random in the margin totals, in the row totals or the column totals. And so then if you pick a cell of this table, it will necessarily have a hypergeometric distribution. So perhaps the first time you saw Fisher's exact test, it was a little puzzling why we conditioned on the row totals and the column totals. But if you frame this in terms of Fisher's sharp null hypothesis, then you see immediately why we would think of the column totals as fixed. This is this is an example of what more generally would be a randomization test. The concept's very general, and we see this in many different examples: permutation tests, exact Wilcoxon tests, exact Cochran-Mandel-Hensel tests, and so on. And the justification for these is not always framed in terms of potential outcomes, but that is one way to think about what these tests are doing as testing the sharp null that there are no individual causal effects. What's appealing about this randomization-based inference approach is you're really making very few assumptions. I didn't get into this, but there's an assumption that causal inference folks call SUPA, which we're making. But really, aside from SUPA and the assumption that we have a randomized experiment, we're not making any other assumptions. No assumptions about sampling from a larger population. These approaches give us inferences that are at least internally valid. So that's just a brief introduction to randomization-based inference. Now I want to shift gears and talk about large sample frequentist inference, which is the more dominant paradigm. So now instead of thinking of our population of interest as finite, we think of it as infinite. And we typically assume that we observe n independent and identically distributed copies of y-obs and x, where y-obs, again, is related to the potential outcomes by this causal consistency relationship. And then we redefine our average causal effect, in this case, as the expected value of the individual causal effect in the superpopulation, or if you prefer, a difference in counterfactual means. What would happen on average if no one was exposed compared to what would have happened on average if everyone was exposed in the superpopulation. And then this is the basic setup, and then perhaps under additional assumptions, we're going to use standard large sample frequentist methods to draw inference about either the average causal effect or these counterfactual means. So one additional assumption that we would typically make if we were doing a randomized experiment is that we would be willing to assume that the treatment assignment is independent of potential outcomes. This is sometimes called a strongly ignorable assignment mechanism. This implies a slightly weaker independence assumption that X is independent of the potential outcomes marginally. But in either case, under a randomized experiment, we would expect this to be true. So if you're thinking of a randomized experiment, at baseline, individuals have two potential outcomes. You flip a coin to decide whether or not they get treatment or not. That coin has nothing to do, whether or not it comes up heads has nothing to do with the potential outcomes. It's important to note that this does not imply that X is independent of the observed Y. And in fact, if X has an effect on Y, then we wouldn't expect in general X to be independent of the observed Y. But if it is a randomized experiment, we would expect X to be independent of the potential outcomes. So under the ignorability assumption, it's easy to show that Neyman's estimator is a consistent estimator for the average causal effect. So I won't bother going through the proof here. It's just simple sort of graduate level 101 stat theory. But the point is that if you do a randomized experiment from a large sample frequentist perspective, Neyman's estimator is consistent. So again, we come back to this same sort of result, which says that in a randomized experiment, association is causation. So this means that if you do something really simple, you'll get the right answer. So for example, if you fit a regression model of the observed outcome on X, then on the left-hand side of that regression model, we could rewrite that. So the expected value of the observed outcome given X, well, that's the expected value of Y of X given X equals X. And why is that? Because conditional on treatment being little x, the observed y's are just equal to the potential outcomes y of x. And then by ignorability, x is independent of the potential outcomes, so this would equal the marginal expected value of y of x. So what that implies then is that the coefficient on the treatment variable can be interpreted up to a negative sign as the causal effect. Okay? So in other words, you do a randomized experiment, you just run simple linear regression without even thinking about it, and you're going to get the right answer. In fact, if you do this using least squares, you just recover Neyman's estimator. Okay, so again, the take-home message is in a randomized experiment, association is causation. You just do something simple and you get the right answer. Okay, so that leads to the question then, what about observational studies? What do we do in studies where the treatment assignment, the exposure is no longer under the control of the investigator? And so in this setting, the ignorability assumption is questionable. And we probably would prefer to not make that assumption. What we worry about is confounding. And lots of people have defined confounding in a variety of ways. Here I'm going to use the definition that Hernon and Robbins give in their book, which they describe confounding as the bias that arises when the treatment and the outcome share a common cause. I don't have the time to go into these directed acyclic graphs or DAGs, but I've included a few here because I think even if you don't understand the finer points, they can provide intuition. So this confounding is described by this graph where we've got this common cause C, which is having an effect on X and on Y. And because of that, it induces an association between X and Y in our data, which is not necessarily causal. So suppose, for example, X is carrying a lighter, C is smoking, and Y is lung cancer. So if you're a smoker, that makes it more likely you carry a lighter, also makes it more likely you get lung cancer. And then in our data, if we had copies of X and Y from the population, we might see an association between individuals carrying a lighter and lung cancer, even though carrying a lighter does not by itself cause lung cancer. Or maybe X is birth order, C is maternal age, and Y is Down syndrome. We might see an association between birth order and Down syndrome in the population, but that's just due to the common cause, maternal age. Older mothers are more likely to have children that have Down syndrome, and older mothers are more likely to have had previous kids. What we do then in observational studies is make the following assumption. We're not willing to assume that it's as if we had a randomized experiment, but what we might be willing to assume is if we had the right set of covariate Z, if we have maybe a rich enough set of baseline covariate Z, we might be willing to assume X is independent of the potential outcomes conditional on Z. So maybe I think exposed folks tend to be older, maybe they're less healthy, and I don't know, they're male in my study. But maybe, and so therefore, their potential outcomes might look different than unexposed folks. But maybe I'm willing to assume that once I condition on age and health status and gender and other covariates, that within strata defined by baseline covariates, that exposed and unexposed folks are exchangeable. Or in other words, that the treatment is independent of potential outcomes. So this is the workhorse. This is like the main assumption people use when they do causal inference with observational data. I'm not saying that there aren't other methods out there, but this assumption is commonly made. So what this means then is that given covariates, the probability somebody is exposed is independent of their potential outcomes. So this conditional probability then just simplifies to the probability you get treatment given covariates. This fellow on the right that I've highlighted has a special name. This is referred to as the propensity score. And it features in a lot of causal inference methods for observational studies. All right, so how would causal inference work then under this conditional ignorability assumption? So suppose now that you fit a parametric regression model, but because this is an observational study and you're worried about confounding, you're going to condition or adjust on not just the treatment, but the covariate Z as well. So maybe you fit a regression model. Here I've written down a model that doesn't have any interaction terms. So then by causal consistency and conditional ignorability, it follows that the left-hand side of this expression, which is given here, you can replace y obs with the potential outcome y of x, because we're conditioning on x equals little x. And then by conditional ignorability, we can drop this term. So you can interpret then the left-hand side as the counterfactual mean of y of x, given you're in Strato defined by z equals little z. Because there's no interaction term, this implies that you can interpret, again, the regression coefficient on x as the causal effect. And so this suggests that if we want to estimate the causal effect in an observational study, we run this regression model, read off the estimated coefficient of treatment as an estimator of the causal effect. And so you're thinking, well, this is good news because I learned how to do regression when I took a statistics course. So I know how to do causal inference with observational data now. I just need to put the covariates in my model. Well, that's true in so much as that this model is correctly specified. And what's missing here is an interaction term. So this model makes a very strong assumption that would probably be dubious in many settings, that the treatment effect is the same across levels of the covariate. So if that really strong assumption holds, then yes, you can interpret the regression coefficient on x as estimating the causal effect. Otherwise, there's no guarantee that you're getting the right answer. This leads us to what's called the G formula, which is a common approach used in causal inference. And it derives from the expressions given here on slide 32. And basically what this says is just through very simple arguments, I can write the counterfactual mean by the law of total probability and conditional ignorability by this expression. And the expression highlighted on your screen is all in terms of observable random variables, y ops, x, and z. And so from a statistician's perspective, that means these quantities would be identifiable. And that suggests that a plug-in estimator for the counterfactual mean, namely fit a regression model, perhaps like one on the previous slide, but maybe with interaction terms. Based on that regression model, estimate this conditional expectation for each person. And then we need to estimate the marginal distribution of the covariates. And plugging those pieces, both of those pieces in, we get then an estimator of the counterfactual mean. So this is sometimes or often called the G formula. So what often is done is the distribution of the covariates is left non-parametric. So we just put mass 1 over n on each of the values of z. And then we estimate these conditional expectations with the regression model. So in other words, you fit your regression model, then based on the regression model, for each person, you estimate or predict what their observed outcome would have been had possibly countered the fact they received little x. You do this for everybody, all in individuals in your data set. Take an average of those, and that gives you an estimate of the counterfactual mean. Another common approach is in observational studies is to use IPW, or inverse probability weighted estimators. And in the interest of time, I won't go through this slide carefully, but basically what this slide shows is that you can write the counterfactual mean, the expected value of yx, this in terms of the first expression here on the slide, which is the expected value of y obs amongst those who get little x divided by the probability x equals little x given z. So for little x equals 1, we're just taking the observed outcomes in the treated folks and dividing it by their propensity score. So this suggests estimators of this form, where you take, if you want to estimate the counterfactual mean had everybody received little x, you take a weighted average of the observed responses amongst folks who got little x, and you inverse weight them by the probability that they received little x given their covariates. This is, if you're familiar with survey sampling, this is has a kind of a Horwitz-Thompson type form. These estimators tend to be quite variable. And so what's often done instead is a Hayek type estimator is used, which basically replaces the 1/n out front with a piece that's more stable, or results in an estimator that has tends to have less variance. These propensity scores, the pieces in the denominator here, say that piece in the IPW estimator, these are typically not known in observational studies, so we have to estimate them. What's traditionally been done is something like logistic regression. So you fit a logistic regression model where the exposure, X, is the outcome, and the predictors are your covariates. And then based on that fitted logistic regression model, you estimate these weights, and then you plug those in, and you construct your IPW estimator. More recently, people are using fancier things like machine learning. Instead of logistic regression, you estimate these propensity scores and then plugging those in. So here's an example from the arthritis literature. This is a study that was published in Lancet 2002, cohort study, and they're worried about confounding. So they fit a Cox model, and they want to estimate a hazard ratio. But to do this, they're going to use inverse probability of weights. And these weights are used to adjust for confounding. And this is a direct quote from the paper, where the estimated weights are the inverse of the patient's probability of having the treatment history they actually would have had. So this is a slightly more complicated example, but it's at simplest form, it is exactly what we're talking about in terms of IPW estimators. This example is slightly more complicated because the exposure is time varying, and we don't have time to get into this in detail. But I just did want to give you a little bit of a flavor of how one thinks about this when you have a time varying exposure. So now in our graph, time here is going from left to right. We've got an exposure at time 0. Maybe that affects covariates at time 1. And then depending on the covariates values, that affects the exposure or treatment at the next time point, and so on. And so in this case, this graph could represent a randomized experiment in that there are no arrows into X0, which would indicate that we've randomized at baseline, and the only arrow into X1 is from Z1, so maybe randomization at the second time point depends on observed covariates. But the point here is that if you think about traditional methods, like say fitting a Cox model with time-dependent covariates, it's not going to adjust for confounding, even in this simple situation, because the time-varying confounder here at Z1 is affected by prior exposure. And basically what that means is that if you fit a naive model where you don't make any adjustments, then that analysis is potentially subject to confounding because you have this backdoor path X1, Z1, U, Y, which potentially could induce non-causal associations in your data. On the other hand, if you adjust for Z1, say you fit a Cox model with a time-dependent covariate, then you are potentially conditioning out some of the effect of X0, right? So part of the effect of X0 is mediated through Z1, through the path X0, Z1, Y. In addition, when you condition on Z1, you open up the path X0, Z1, U, Y, and potentially induce a selection bias, which will also cause association, non-causal association in your data that would bias your results. So I've introduced two methods, the G formula and IPW, that are used for causal inference in observational setting. To do these, we have to estimate either this conditional mean of the outcome or propensity score. And if, in fact, you can show if you do both of these completely non-parametrically, then the estimators are equivalent. But if Z is a vector of covariates, if it contains continuous covariates, it won't be possible to do this non-parametrically. In which case you would be introducing different parametric assumptions depending on which of these approaches you used. And of course, the validity of your inferences would depend on those parametric models being correctly specified. There are so-called doubly robust estimators out there, which combine IPW estimator and parametric G-formula estimators. And they give us the benefit of providing valid inferences, provided at least one of those two models is correct, but not necessarily both. And that's why they're called doubly robust estimators. This is an example, again, another arthritis study where they used one of these doubly robust estimators, which they describe as combining the advantages of a regression model and an IPW, and it will produce an unbiased, here I think they mean consistent, estimate if either of the two models is correctly specified. And fortunately, we're coming along now in an era where a lot of these methods are programmed up in standard software. So for this paper, they just use the DR command in Stata. And many of the methods that I'm talking about are also available in SAS and R and other standard statistical software packages. Let me say a few more words about the propensity score. So one result, so the propensity score was first described in this paper by Rosenbaum and Rubin in 1983. And one of the key results from this famous paper is that if you have conditional ignorability, or what's also called the no unmeasured confounders assumption, if that holds, then it will also be the case that treatment will be independent of the potential outcomes given the propensity score. So what this means is that it will be sufficient to adjust or stratify or control for confounding just using the propensity score, which is just a scalar. It's just a number of random variable that lives between 0 and 1. And that seems like it would be a lot easier than having to adjust for Z, which potentially is multidimensional. So that this fundamental result has led to numerous methods that utilize the propensity score and leverage this finding. So for example, one idea would be to stratify individuals according to their propensity score. And so then within strata, remember this fundamental result says that within strata defined by the propensity score, the treatment assignment is independent of the potential outcomes. So within those strata, it's as if we have a randomized experiment. And we know in randomized experiments, causal inference is easy. Association is causation. So you stratify individuals according to their propensity scores, estimate the effects within these strata. Those are going to give you valid estimates of the causal effects within strata, then take some weighted average of those effect estimates across strata. A related approach is propensity score matching. And the idea there is you find a treated individual, you figure out what their propensity score is, and then you find an untreated individual who has the same propensity score, and you match them together. And because they have the same propensity score, it's as if you did a randomized experiment with those two individuals and randomly assign one to treatment and the other not to treatment. And so then once you have this sort of matched data set, really simple naive analyses will, in theory, give you the right answer. So this is another example of an arthritis study where they used this propensity score matching. They were worried about potential bias and allocation to which drug or treatment individuals received. So this is, they were worried about confounding. So they took the individuals in this observational data set and they matched 1-to-1 each treated individual to a control individual. That gave them a subset of the original data set. And then with that subset, they just did really simple analyses, like a paired t-test, to see if there was a treatment effect. As I mentioned, many of these methods are available in standard software now. For example, SAS has a causal treat that came out recently, which allows you to implement IPW estimator, G-formula, and doubly robust estimators. In R, there are many R packages out there now. G formula came out recently. Matching package has been out a decade. It's a well used package, and so on. And as I mentioned before, the real workhorse here is this conditional ignorability assumption. One question you might ask is, how do you choose the covariate Z? That's sort of a whole different discussion. Of course, whenever we do this, we always worry that there's some unmeasured confounder that we haven't included. So if we go back to our DAG, we've got covariate Z. I put a box around them, meaning we have observed them and we're adjusting our conditioning on those. So we're controlling for confounding due to the XZY path. But you always worry that there's some other variable out there you didn't measure, which is a common cause of X and Y, which could induce unmeasured confounding. So that's sort of the Achilles heel of a lot of these methods, that one always kind of has to worry about that in the back of your mind. There are sensitivity analysis methods that have been developed to assess robustness of inferences to violations of this assumption. People have also worked out bounds or sort of partial identification results. And then there are alternative approaches which rely on different assumptions in order to draw causal inferences. And it's sort of a trade-off. Maybe you're not willing to make the no unmeasured confounders assumption, but you are willing to make one of these other assumptions. So these include things like instrumental variables, negative controls, and the front door criteria. Other sort of extensions or directions, we've been talking about X as a binary covariate. You may be in a situation that has multiple levels, in which case for each person we would envisage multiple potential outcomes. We may have treatment varying over time, as in that Cox model example I gave earlier, in which case we would index the potential outcomes by the vector of treatment over time. If X is continuous, then we would think of individuals as having an infinite number of potential outcomes. Another active area of causal inference that's widely applied is mediation analysis. And so there, if we take the potential outcomes framework, we would index the potential outcomes both by the exposure and by the putative mediator. I know we're running short on time, so I'll just wrap up. So that's a summary of causal inference from the potential outcome perspective, touching on randomization and large sample frequentist inference. Again, kind of the take home is that in randomized studies, we get the right answer. Association is causation. In observational studies, what we typically do is assume that conditional on covariates within strata defined by covariates is as if we had a randomized experiment. And then the slide deck here includes some additional resources. There's a causal inference course offered in the Department of Biostatistics every year, every 2 years, called Bio 776. For that course, we use the Hernan and Robbins book, which just came out, called Causal Inference What If. This book's actually freely available as a PDF right now. I don't know if it always will be, but it's you can go to this website and grab it. One thing that's nice about this book is they have code, R, SAS, Python, and so on, to duplicate all the results in the textbook. And then a few other pretty famous causal books. Paul Rosenbaum's Observational Studies book is very nice. Morgan and Winship is an accessible overview of many different areas of causal inference, including DAGs, potential outcomes, and so on. Emmons and Rubin wrote an influential book, came out in 2015, very comprehensive. Pearl's book is the book if you're interested in the graphical approach to causal inference. And I'll leave you with a few references and stop there.
Great. Thank you, Dr. Hudgens. So we have some time for a couple questions. So just to remind everybody, you can type your questions into the chat box if you have one. And I guess to start, I have one about, can you explain again why we can't just use multiple linear regressions to adjust for confounding?
Sure. So, I mean, the answer is you can, if you're willing to assume that there's no interaction between X treatment and your covariate Z. So if you think that there's no, essentially no effect modification, that the effect of the treatment doesn't change according to levels of the covariates. So if this regression model is correct, that there are no interaction terms, then you can just read off the estimated regression coefficient on X as a valid estimate of causal effect. But it really relies strongly on that assumption of no interaction. And otherwise, if you do have interactions, alpha 1 no longer has, can be interpreted as the average causal effect. In that case, alpha 1 would be interpreted as estimating the average causal effect for individuals whose covariates are equal to 0, whatever category, whatever that means in your context. Otherwise, if you're looking for an approach to draw inference about average causal effect using regression, then one needs to use the G formula instead. Todd says, can you comment on any challenges in terms of publishing in clinical journals using these methods? So I would say that it's becoming, these approaches are becoming a lot more mainstream. So I think 20 years ago, if you published a paper and you said you used a marginal structural Cox model with inverse probability weighting, you may have had reviewers asking you what you were talking about. But now these methods are well established. As I said, they're baked into SAS, and they're just very common. You see them everywhere. You see them in the statistical journals. You see them in the subject matter journals. So I think that there will be less resistance to these, to getting these approaches published than in the past. And in a lot of ways, these are the right methods to use if you're trying to answer a question about what is the effect of a treatment or exposure. Whereas if you use traditional methods, it becomes a little less clear how to interpret the results. And I think these methods make it very clear how, in terms of interpretation. Todd's second question was about how this relates to precision medicine. And I did have a few extra slides to tie this into precision medicine, but I know we're over time. So I'll just say that, the idea behind precision medicine is, to offer treatment, to give treatment only to those to whom it'll benefit. So whereas the approach that I described today, we were thinking about settings where everyone got treatment versus no one got treatment. But in precision medicine, we ask a slightly different question, and we say, what would be the best way to assign people treatment? And ideally, you would give treatment only to those individuals for whom it benefits. Now, of course, ahead of time, and maybe if you're a really, really good physician, but ahead of time, we may not know if an individual will benefit or not from treatment. But we might hope that based on existing data, we could predict who's going to benefit from treatment based on their covariates. So you could think then of a different policy or regime, which essentially is a rule or function, which tells you, given somebody's baseline covariates, do you give them treatment or not? And so the area of precision medicine is basically developing statistical methods to find that optimal treatment rule. Because you're thinking of, in precision medicine, individuals having two potential outcomes in the simplest case, one if they receive treatment, one if not. This is really just a causal problem. So one view of precision medicine is that it's kind of a sub-area of causal inference.
Okay, thank you, Dr. Hudgens, for taking the time to talk with all of us today. We'll be sending a follow-up email to everyone in the coming days with a link to access a recording of this talk in case you would like to listen to it again or share it with your colleagues. Please join us again in 2 weeks on May 27th at 9:30 when our speaker will be Dr. Jennifer Lehman. She'll be presenting an introduction to implementation science, speeding the translation of effective interventions to wide-scale practice. Thank you for attending the talk, everyone, and I hope everyone has a wonderful day.